Today we're kicking the meeting today with Ben Kroposki, who is at National Renewable Energy Lab. He is the director there on the Power Systems Group, has been long-term leader and visionary in the area of innovation at NREL. And he will tell us about his vision and a vision of your team on the open questions as you see them and some possible approaches. So please welcome Ben. You saw the more elaborate abstract in the announcement, so I'm not going to spend time on that. Just one logistic thing is that you can raise your hand and ask the question if it's a burning question, but I think it would be sort of better to put your questions in chat, and at the end Ben goes through them. Okay, Ben, it's all yours. Thank you.
Okay, Dan, did you want to say anything before we get started?
I should have introduced Dan. Dan is my partner in crime. We are co-organizing this together. He's a postdoc at MIT, so we talk a lot at MIT about open questions and how a lot of theoretical scientific things needs to be connected with practical problems and so forth. So I very much enjoy working with him. So Dan, you want to just say anything about yourself or?
Oh, hi. I'm Dan Wu. I work with Maria, and my research is on the multi energy systems, including the electric power system and also the natural gas system. So yeah, it's fine. Oh, by the way, I'd like to mention that this presentation will be recorded, and so we're trying to make this available online in some ways, and we will announce it later.
Right, so it probably would be better to mute yourself, and we'll mute ourselves so that the sound is the best, unless you want to speak. Thank you very much.
Okay, I'll go ahead and get started, and thank you very much for having me talk at this seminar series today. My name is Ben Kroposki, and I'm going to be talking about the need for grid-forming inverters in future energy systems. So let me switch over to my presentation here. Okay, hopefully you can all see this.
Yes.
Again, thank you. My name is Ben Kroposki. I'm the director of the Power Systems Engineering Center at the National Renewable Energy Laboratory out in Golden, Colorado. But I'm also serving as the organizational director for a new consortium that we call the Unified Consortium around universal interoperability for grid-forming inverters. But let me start off with a bit broader idea and question about what's going on in the power industry right now, and discuss the need for grid-forming inverters in the current power system and as we migrate into the future power system. And specifically, why I think this is really the most critical topic that we need to address in the near term to achieve the 100% clean energy goals. So just to step back only 1 year, 2020 really was the seminal year in the energy industry for a lot of reasons. So if we take a look at sort of the energy supply that has been happening for the last 70 years shown on this graph. So this is data taken from EIA, shows you the amount of energy that is consumed in the United States by different technologies. And one of the things that you can see here is probably for the last 10 years, coal has been on this decline in use. And that's being replaced with natural gas and renewables. And so natural gas and renewables have increased during that time. Nuclear and hydro, they've remained pretty steady over the last 10 years. But 2020 was the first year since 1950 on this graph that renewables surpassed either nuclear power or coal as a form of energy generation in the United States. So with 20% renewables, this is a significant milestone. Now, if we dig into this 20% a little bit more and break it into its components, you can see here in this particular graph, the bulk of this is hydroelectric power shown in blue there. But we are seeing increases in solar and wind. And again, in 2020, we can see as we look at the breakout here, 8.5% of the energy was supplied by wind. And this is the first time that wind has produced more energy than hydroelectric power. And then we can also see the rapid increase in solar. So solar and wind is just rapidly being integrated into the power grid as we know it, producing more and more electricity. So why is that happening? If we take a quick look here at this particular graph, we realize that this is usually what drives practically everything in the world is economics. And the cost of renewables has been declining considerably. So as you can see from this particular graph, solar has gone down tremendously, over 90% decline in the cost of solar since 2009. And wind has also gone down 70%. But right now, in terms of if you were to go out and install a new plant, wind and solar are the most cost competitive forms of electricity. Now, of course, you do have to have the wind and solar resources available to make these economics work. But in general, as an average across the United States, as you can see here, solar and wind are the most cost competitive forms of electricity. And these are really driving this massive installation of wind and solar because they can produce electricity for such low cost. The interesting thing is that even though these are the costs for new plants and compared to other plants like nuclear, coal, even natural gas, which are a little more expensive if you were to build a new, these pricing numbers are really producing electricity that's rivaling existing nuclear and gas plants and are below existing coal plants. And this is why we're seeing a massive retirement in the coal fleet, because we can go in and put brand new wind and solar plants that are making electricity for less than existing coal plants in a lot of cases. So the other thing that's driving the increased use of renewables is states and utilities setting clean energy targets. And we see this more and more, a majority of states around the United States have a renewable portfolio standard where they're trying to reach a certain amount of renewables as a percent of energy over time. But what we're seeing is more and more of these places actually setting very high targets. So we're seeing places setting 100% clean energy goals. As you can see here, the blue colors are the states that have these significant targets. And then the green shaded areas, these are actually independent utilities. And so a utility can stretch across multiple states. For example, here in the Southeast, Duke Energy covers both North and South Carolina. They've set a 100% decarbonization goal by 2050. Other utilities, like our local utility here in Colorado, Xcel Energy, although Xcel Energy owns parts of the utility grid in Colorado, in Minnesota, and in Texas, they've also come up with these 100% decarbonization goals. So this, again, is another driving force behind the increased use of renewable technologies. The other big thing that's happened recently is the new Biden-Harris administration setting what I would consider very aggressive targets. So they want to get to 100% clean electricity by 2035. So if you think about the entire electric power grid and some of those graphs that I showed you before, that means significantly reducing the use of coal and natural gas, fossil fuel carbon emitting sources, or adding in carbon sequestration with those sources in the next 15 years. So that means the next 15 years in the power system industry is going to see a massive change if we can keep moving toward these goals. And then they have an even more aggressive 100% clean energy economy, which would include transportation and industrial sectors by 2050. But if we think of what does that really mean, if you take a look here and kind of a thought experiment, 100% clean electricity, if we can use the 20% nuclear fleet, the 7% hydro fleet, maybe we got 10% of clean, futuristic hydrogen fuels or something like that, that still means that the power system in 2035 is probably going to need to have between 50 and 70% wind and solar by energy. And so that means we're moving from 10% to 50 to 70% in 15 years. And that's a big, big change. But it's doable, but there are some key things that we need to address to get to there. So let's talk a little bit about sort of what we know when we think about how the grid works with high levels of renewables. This is a little series of charts that I put together there. They kind of explain where we are as a situation across the grid right now. So if we think about what you're looking at here at system size in gigawatts, from very tiny systems that could be 100 kilowatt size to megawatt size to tens of megawatts to gigawatts to 1,000 gigawatts is the installed capacity that we have in the continental United States. And then percent wind and solar along the y-axis. So for small island power systems, this is a picture of Tau Island. It's in American Samoa in the Pacific. They actually run this as what I would consider 100% renewable grid, where they have large-scale PV systems, large batteries, and can run that grid at 100%. Both, and two important numbers here to differentiate. One is an instantaneous level, so any particular point in time, they can run it at 100% solar and battery. And then on an annual basis, over the entire year, that's what this gray circle represents, is the percentage of that. So as you can see several islands here, the key factor among all these islands is they have significant amounts of energy storage and oversized generation in relationship to their load. So here, 150 kilowatt load has got a megawatt of solar and megawatts of battery energy storage attached to it. But we know how to design and operate these small independent systems at really high levels of renewables. If we kind of go up in size, this is where a big focus right now is larger island grids and trying to take these closer and closer to 100% renewables. So the Hawaiian Islands are on this path right now, where we've deployed a significant amount of wind and solar on Kauai and Maui. They're operating right now on a 40% annual energy basis and instantaneously up in the 90%. And then a bigger system, this is about a 6 gigawatt peak, is the country of Ireland, operates around 30% wind and up to 65% instantaneous. But recently, they've actually pushed the limits on these, and you can see here, both earlier this year, we're able to achieve close to 90% on Maui instantaneously, and 70% instantaneously on the island of Ireland. And then if we look at larger interconnections, so in the United States, we have 3 large interconnections going from smallest ERCOT to the next largest, the Western Interconnect, up to the Eastern Interconnect. You can see that we're, especially in ERCOT, pushing the limits of how much renewables we can get. Right now, they're about 26% wind on an annual energy basis. And in fact, earlier this year, just reached 66% on an instantaneous basis across the system. Of course, that was just for an hour, but they're incrementally getting higher and higher instantaneous levels of power into the grid from renewable sources. Now, here's kind of a summary across this, but at the end of the day, the key things that we need to be able to do is we need to try to take these large-scale power grids and get them to operate similarly to what we can do on small-scale power grids. And we need to come up with technical solutions to get these large grids to operate closer to 100% inverter 100% inverter-based instantaneous levels in these large-scale power systems by unifying the operation of inverters with synchronous generators. That will allow us to get these average annual energy levels above 50%. Remember, I was saying we need to be up around 50 to 70% on an annual energy basis from wind and solar across the United States. But let's see why getting to 100% inverter base is really important. So if we take a look at the country of Ireland, as I mentioned here before, if we go back and look at the 2018 data, they were 30% on an annual basis, 65% instantaneously. Let's take a quick look at this data and try to keep pushing that number here from 30 up to 70%. At the same time, we want to get to 100% instantaneous. And so let me explain the reason why we want to try to push those limits. Okay, so if we take a look at some data here, this is going to be some back of the envelope calculations, but you take a look at Ireland in 2018, you can go download this data from AirGrid, the system operator, but this is showing you wind output and percent of wind energy across the entire Ireland grid from January to December across an entire year in 15-minute increments, which is either limiting it right now to 65% instantaneously. If we need to get to 70% on an annual energy basis, we need to install more wind. And so to just simplify things, what we did was just install it at the same locations and bump up the amount of wind. But you can see here quickly, this blue line is basically it gives you enough energy to give you 70% on an annual basis. But all of a sudden, we're going way over 100% instantaneously, a lot of hours in the year. Let's reorganize this data a little bit so it can be a little bit easier to understand. We're going to create a duration curve. If you've ever heard of a load duration curve, what you do is you take the data and information, you then resort it from high to low instead of chronologically like we have here. So we're going to just resort this data like that. And then we create this line. This line now represents the high to the low in the number of time periods. But this is now a percent variable renewable duration curve. This helps understand really if we now take that for both the 30% annual energy wind, which is what they have existing, and this new curve, which is 70% on an annual energy basis from wind. Now, if we take a look at here at these horizontal lines, you quickly realize, well, if we just start limiting, if we kept that limit at 65% instantaneous, we would come up with this situation where we would have 30% annual energy from wind, and we have to produce the rest from other sources. But now if we maintain this limit here, we have an issue. Because even if we installed lots and lots of wind turbines, we basically would have to curtail at this point, and we would lose out all of this energy right in here. We gain this piece right in here, and that increases from around 30% to around 45% by adding in this piece. So by increasing the amount instantaneously up here, and then you would still have to provide other sources to get this. But if what we needed to do was come up with a technical solution that allowed us then to push this line up to 100% instantaneously, you can see what we would pick up here is this piece of energy. And so that by picking up that piece of energy there, you can see we've now increased the total amount from 45 to 58% for the Irish case. We still have this piece that we probably would have to curtail or load shift or something. So there are options to do that. But just moving from these self-imposed limits of 65% to operating grids with 100% inverter-based resources, we can get annual energy levels, that are now in this 50 to 70% range that we need to get to. This is also a challenge. There's a lot of things that we can do to try to address this. Things like adding system flexibility with energy storage, increasing the transmission, adding load when we have high levels of wind, a variety of solutions there. But I just wanted to make sure I pointed out that one good, quick way of getting a bunch of energy that you would nominally have to curtail is to allow getting up to 100% inverter-based grids. Okay, so that's why we're really focused here on understanding sort of these machine and inverter interconnections and how they work together. and how to make sure that the machines that the grid's been based on and how these new inverter technologies can seamlessly work together. If you think about how the grid works, right now we have large-scale interconnections of synchronous generators. So whether this is a hydro plant, nuclear plant, coal, natural gas, they actually all interconnect together through the electric power grid and create basically a large-scale virtual machine that's all synchronized together, working at the same frequency, that's providing that 60 hertz AC waveform in the United States or 50 hertz in Europe. When we connect induction machines or inverter-based technologies, they don't have the same physical characteristics as a synchronous generator does. And so they don't really have this tight coupling that appears when you connect synchronous generators together. But what we need to do is develop inverter-based technologies for wind and PV systems so that they actually can operate similarly to synchronous generators. They're not going to be exactly the same as a synchronous generator, but we need to make sure that we can unify that operation between synchronous machines and inverter-based resources at any scale. And this will enable us to put any amount of synchronous generators or inverter-based technologies together and operate cohesively. So there are a variety of technical challenges that need to be solved in this space. At a high level, I kind of showed you that picture there around things like frequency stability and why we need to make sure that we come up with advanced controls for inverters that ensure frequency stability and voltage stability across large-scale power grids. There's additional challenges, things like system protection. That can best be kind of understood by looking at this graph here. So system protection is basically how we design the grid and protect it from fault conditions. But just to point out some examples here, if you take a look at different fault characteristics, so these are output curves from a fault when it happens here at this time. For a synchronous generator, when a fault condition occurs, you would get this really large scale spike in output current, and then it sort of declines over time. But typically this is a pretty big spike, and this is how we often use overcurrent protection. We can recognize this really large bump in output current provided by synchronous generators. Inverters, on the other hand, don't typically have that capability. And so you can get a variety of outputs when you fault an inverter. You can get them to react very quickly, as in this red line here, where they detect that fault condition happening and disconnect in a quarter cycle down to 0. Or this inverter could ride through for several cycles in this case and then trip off. But in either case, you know, either of these lines do not look like this large amount of fault current provided by synchronous generators. So new protection schemes really need to be designed around how we incorporate inverters and recognize fault problems on the grid. Additionally, and we'll dive into this a little bit more, this grid forming capability. If you think about the grid, it has to sort of be protected from, or you have to have devices on the grid that can actually form that AC waveform. If you just have grid following inverters at a certain level, your grid following inverters, you know, won't be able to produce an a reference AC waveform to allow everything to synchronize together too. So that's one of the key aspects of that grid forming capability. Another piece is the black start capability. So understanding, for example, if the grid goes down, how can we restart the grid? Typically we do that right now with diesel gen sets that start up power plants that then reconnect the rest of the grid piece by piece. But if we have a 100% inverter-based grid, can we actually restart the entire system using a variety of techniques to look at that? And then there's other things to think about in terms of control system interactions and potentially new resonances that may occur from all these power electronic devices, and then finally cybersecurity concerns. So there are a number of challenges to us getting to these really high levels of inverter-based resources, although I would say they're all manageable, and we can come up with solutions here, and we need to come up with solutions in the very near future to get to these high levels of renewables. I wanted to point out that, you know, I had talked about 100% renewable grids, and we know we can make them on a fairly small scale and have them operate properly. This is an example. We actually had a system failure at one of our site locations. This is our Flatiron campus where we do a lot of our wind turbine testing. And we had an issue with one of our substations there going out, but we were actually able to demonstrate that we could set up a 100% renewable grid using a 1.5 megawatt wind turbine, a 450 kilowatt PV system, a 1 megawatt battery, and then actually run that system. We ran it for 72 hours, the entire building loads for this particular system. And we were actually demonstrating some advanced new control techniques that allowed these all inverter-based resources to come on site and actually do load sharing amongst them while they had it operated. You can see during the daytime here, this is the PV output in orange, the wind output here in green, highly variable, but we're using the battery system, this blue line, to absorb a lot of that variability and provide the power to the load, which is this gray line across here. But we know that we can make 100% inverter-based grids. We do need to figure out how to make them at much larger scale. So migrating from this megawatt example here to, you know, gigawatts in size. Okay, so I kind of laid all the background for why we think it's important to develop a consortium that really focuses on grid forming inverters and the idea of how to get inverter-based resources to operate at any level in the power system itself. So the Unified Consortium is what we recently put together. This was recently awarded as a project from the Department of Energy. We're in the process of negotiating that project now and hope to kick it off here in January. But the idea here is that future power systems will be available with any mix of machines and inverter-based resources at any scale. And as I kind of explained this graph in the other areas, you know, our big thing is to address the fundamental challenges of integrating grid forming technologies and other inverter-based resources and migrating from this curve here to push that up so that we can get as close to 100% instantaneous across the grid at any particular time for very large scale power grids. And we need to conduct the necessary research and development, demonstrate these concepts at scales, put together best practices and standards in this space, and train the next generation workforce, because the grid of the future is going to look significantly different than the current grid that we have. And we're going to do this change fairly rapidly. If you think about, you know, we've built the grid over the last 120 years, but we're about to transform it in the next 15 years. And to think about, you know, this isn't an unsolvable problem. If you think way back to the early 1900s, when people were really just starting to put together large power grids. You can see this meeting picture here is a joint meeting of the Institution of Electrical Engineers and American Institute of Electrical Engineers, the precursors of what is now IEEE. They were getting together and having meetings around trying to understand how to parallel synchronous generators. And so they were developing all of the information and rules of the road of how we parallel synchronous generators together, maintain stable and reliable operations. And what they did was created the large-scale power grids that we know today. And so this, you know, engagement between the researchers and practitioners is critical. We also need to provide a platform for migrating the same kind of thought process here for integration of inverter-based resources with the synchronous generators of today that we have. So we see this being a way to integrate all of this together at the end of the day. And so this consortium really will focus on unifying the way that we operate grid forming technologies and grid following technologies with synchronous machines. It'll unify local controls that are happening inside these inverters with the global controls from the system's perspective. It'll unify sort of operations at slow and fast timescales. We need to think about how to integrate large inverters, because we have large, power plants, gigawatt scale PV and wind turbine plants, as well as small inverters that are on people's roofs. And then finally, we need to find ways to unify the integration of solar, wind, and energy storage technologies, all inverter-based technologies, with the synchronous generators of today. Just to highlight here, this consortium is being led by NREL, the University of Washington, and EPRI. And then you can see we have a large set of players involved, several national laboratories, 12 universities. And then from industry, we have the inverter manufacturers, a good cross-section of those, and a large set of utilities and system operators that are key to understanding how to deploy these technologies in the grid. And we're also working closely with, you see the real-time simulation and software vendors here, but we're also working with practically every one of the power system simulation vendors. And we're thinking of how we're actually doing all this work. So we have thrusts in the R&D space that would include things like modeling and simulation, advanced controls, how we deploy those inside hardware, and how we integrate those into systems and validate their performance. We also have thrusts looking at demonstration and commercialization, and this would include even large-scale demonstrations, managing the IP and domestic products that come out of this, and finally, how all this information gets pushed into standards. And then finally, outreach and training that would focus on educating both students and the workforce that needs to come into place for these technologies and communications and events. We also have a range of additional partners that have provided support to this, including additional utilities, system operators, vendors, and software companies. And then we're working closely with a lot of the other consortia that are out there, consortia like TCERC, which focuses on the power system side of research, and places like Power America, which has got a very power electronics focus. This particular consortium is kind of a meeting place between the power system industries and the power electronic industries. And we kind of have a very broad scale across the entire continental United States, and even reaching out to Hawaii, Alaska, Puerto Rico, and covering a wide variety of geographic areas. So this particular consortium, is built to really foster this ecosystem of what I've discussed in terms of research and development, demonstration and commercialization, outreach and training. Probably the key feature of this consortium is this middle bullet here, around curating sort of what we're calling interoperability guidelines at a system level and the functional requirements for the inverter level that need to be technology agnostic, vendor agnostic, and standardize the performance of these technologies across any scale, so whether it's small or continental scale deployments of these technologies. And I'll dive into that just a little bit more here. You can see we've started laying out what needs to be included in each of these areas. So as we look at system level guidelines, we want to make sure that we're promoting the seamless operation of various grid forming technologies from multiple vendors to ensure stability and reliability, looking at what type of system level control signals can be sent down to these devices, ensuring that they're maintaining stability, frequency, and voltage regulation, and can they provide things like black start and cybersecure communications. And then at the individual plant level, this is key because this is actually embedded inside each of these inverters, but you need your basically real-time control, your primary control that's working inside based on local signals here, but then also how you're communicating out to the outside world and how you're ensuring stability, power quality, and protection requirements for these type of devices. So just to summarize this, I mentioned before, we have a really large team currently working on this across the national labs, the research institutes, the inverter manufacturers, utilities. This team has worked extensively on developing things like the droop control method for inverters and virtual oscillator control methods for grid forming inverters. we've been doing large-scale demonstrations to date, showing off sort of inverter-based technologies for providing a range of grid services, and the team is very involved on the development of interconnection standards. IEEE 1547 is the interconnection standard for distributed resources, and the new P2800 is going to focus on transmission-connected inverter-based resources. But bringing this entire group together has been key. We really see the fact that at the end of the day, we're using this consortium to unify the integration of machines and inverters in the power grid with the goal of driving the industry toward achieving these clean power goals by 2035. I'll also highlight here, we also kicked off a seminar series. If you're interested, you can follow up and we can get you plugged in, but we've been having weekly seminars specifically on grid forming technology. So we have a pretty narrow focus here. But as you dive into this, there are a lot of details that still need to be addressed. And this consortium is looking at being that focal point across the US for making all of this happen. And with that, I'll say thank you, and we can take questions. So thank you very much.
Thank you very much, Ben. I truly enjoyed the presentation, and this is actually very exciting because the little anecdote it was late 1980s, 1990, 1998, something like that, before I moved to CMU, and I actually gave a talk at MIT. I have one of those tapes, you know, the old-fashioned tapes that it was recorded. It's worthwhile looking at that tape because I gave a talk at MIT about the upcoming challenging problem in the future when you are going to put, at the time, it was more about controlling fax devices at the bulk power system. But now we are talking more about, you know, lower voltage level, but the same type of issues. When you have very fast control, do you need to coordinate them and so forth? And so I think one question that we are going to have to deal with, in particular the younger junior faculty, you know, who have to worry about tenure and so forth, how would you stage this work in the consortium and the participation so that people do both fundamental research and also connect with industry and work closely? At that time, we did not know how to do that. It looked like blue sky, right? And it wasn't the problem, but 20 years after that, it becomes the problem. So I think it's one of the fundamental issues on how to support the innovation and give credit to young people about this. So can you elaborate on that a little bit?
Sure. Yeah. So the consortium really, you know, has been designed from the get-go to be this connection between the researchers that do a lot of work in this space and the industry. And, you know, as we've been developing sort of the statement of work and the proposal around this, there's always been a close tie of having the industry players participate even on the very fundamental research side of this. So, and having them involved and review the work on a very, very regular basis. So, I mean, I think that we see that as being a critical point because we can't just develop something in research and then hope people will use it because that's very slow. And we need, as you can see from my presentation, we have to do this in the next 15 years. There's no time to waste on trying to educate people on things. We need to be working with the people that are manufacturing these products immediately so that they can have things that are ready to be deployed. And that's why if we take a look at sort of our work plan, even though we have all these R&D tasks, the reality is the thing that drives them is this common set of interoperability guidelines and functional requirements. And that's actually going to be evaluated, tested, and put into practice all within, you know, like a 6-month turnaround, and then repeat until we get a lot of consensus on what those actually should be. So that, you know, over the first couple of years, there's going to be a lot of drive to get quick standardization on what those requirements are going to be. And that way industry can start implementing them before the standard. We can't wait for a standard even to be written in this. They need to be implementable inside the control algorithms of these inverters now, that we can adjust as we go through the next couple of years.
That is great. Thank you. I think it's extremely important looking in hindsight, in the way we did things before. So we have some questions in the chat. I don't know if you can see it. The first thing was from Ryan Cummings, who is asking about cost of nuclear. Can you read the question and answer?
Sure. So the question is, how is the, from slide 5 in the presentation, how is the cost of nuclear plants derived if a new operational plant hasn't been completed since 1990? Well, two things on that. So the cost, those costs are taken from Lazard. So if you don't know Lazard, they publish like every single year a costing of every technology, and they do a very detailed analysis if you want to find the details of how they're developing their cost profile. So I would suggest checking that out. But in general, they're going out and looking at two things. They're either asking manufacturers of what they think they can provide. The cost to build a plant is number one. And number two, even though we haven't completed a nuclear power plant in the US, that doesn't mean elsewhere around the world we're not building nuclear power plants. So they can take some of those costs, external to the US, and then kind of convert to what they think that cost might be here in the US.
Okay, thank you, Ryan. I hope this answers your question. Then there is a next question about seeing only AC connection between any resources. What about hybrid grid, which take also advantage of some DC grids, which are connected then to the AC? And I don't know who asked that question, sorry.
Yeah, so that's definitely something that we need to consider. I didn't really talk about it here today, but if you take a look at the overarching requirement needs to access 50 to 70% wind and solar in the continental US, you will quickly come to the determination that we need a pretty big expansion to the transmission grid as it exists today. And so that's where you need to take a look at, okay, if we're going to expand the transmission grid, we should look at AC transmission expansion, DC transmission expansion, and some hybrid AC-DC approach. Now, the people that have the most near-term or recent experience with this hybrid AC-DC power grid is probably the Chinese. They've basically, if you take a look at what they've done, they've basically doubled the size of their power grid in the last 10 years. So we know it's feasible to be able to do. They have developed a couple of new technologies there, going to the 1 MV, 1 million volt AC and DC transmission systems. But there's lots of work that needs to be done to figure out how do we expand the transmission system and what's the most cost-effective way of doing it, whether it's AC or DC technologies.
Okay, so that would be part of research. I want to inject one thought and question here before we go to the next question, which is related to this. So this is a painful point for me, because when we plan transmission grid investments, right, it is very hard at that time scale to take into consideration effect of flexibility and uncertainties and so forth. We just don't have methods to do that now. So that presumably will be big area for research under the consortium. But is there a way to have more interactive transmission planning in which, once we have these interoperability standards, we would actually have aggregates of microgrids commit themselves that they can provide something in a little longer term, so that you offset over design on transmission? And I think a sort of related question to that, which is, I think in my mind is in the heart of things, when you describe the DC grid, that it looked like what Chinese have done. They have done it at the very extra high voltage level. I think here we are talking about a lot of DC technologies, and such exist by some startup things, on interconnecting neighbors with DC connections and so forth, and aggregating them and sort of going end to end, so that you have law of large numbers in which a lot of solar rooftops, a lot of small DRs actually help the bulk power system rather than hurt it, right? So so the fundamental question of how to integrate flexibility as you plan, as we did, I think it's really going to be extremely important. And how do we map it into protocols and standards? It's not just that Siemens gadget needs to talk to ABB's gadget. That's interoperability the way the industry understands it. When you put those two gadgets, they have to work together. They have to be feasible and they have to be stable. And so my plug for this is that really, you know, standards have to be such that they support some provable performance or certain ranges of penetration. And I don't know, maybe you know much more about this, but whenever one goes to the discussions on standards, we don't think about them that way. So is that link going to be made?
Well, I mean, you know, there's kind of a couple of points in there. When we think about system flexibility, there are a lot of options. I didn't really dive into it too deeply in this presentation, but you have to consider, you know, transmission building and expansion as one level of increasing system flexibility. But there are lots of others that you need to consider, things like energy storage, load control, which is a huge untapped potential.
Right.
And just how we do system operations, like you say, aggregating different parts together that could provide their own generation and reliability. The challenge is there's a lot of different options, and it's very difficult to compare them all against each other and decide which is the most effective way of actually implementing those. But the good news is there are lots of potential solutions. You have to quickly figure out, though, which are the most economical to move forward to meet your end goal.
So in power systems, we have this beautiful concept of balancing authority and area control error, which is unified, right? It's total net imbalance, but it is over 10 minutes when you do schedule and so forth. So I think that the only way forward is to say, okay, I have a bunch of very diverse small DRs and neighborhoods and whatever, but seen from the higher level operator, they have to be characterized in terms of something like that, which is generalized. And so if you put a bunch of like 8 gigawatts of power from California and solar and let it connect it to Cal ISO and you don't know what it is, that is real uncertainty. We cannot operate that system that way. So this issue about we've been advertising this, going from balancing authorities, which are huge, to intelligent balancing authorities that characterize themselves so that when you put them together, they work. I think, so I'm trying to put a plug here for more of fundamental rethinking of how we putting this system together so that we don't technology bias.
Yeah, I'll put in a small plug, but don't have time to go into it now. If you Google autonomous energy grids, you can see a lot of work that we've done on that sort of concept of building up small cellular approaches from the very bottom that could work together as you build them in a hierarchy together. Okay. Let's see, jumping back to some of these questions. In the absence of grid forming inverters to push 100% renewables, is there a fundamental limit to how much we can achieve? So in general, it depends what other devices you have online, because you can achieve some of these kind of results if you have synchronous condensers, which are basically going to look like a synchronous generator but not provide real power. If you were just to have grid following inverters only, you will hit stability issues, you know, probably above 75%. If you just are doing grid following without any kind of smart controls associated with it. I think we have some papers that kind of show you where you hit that limit. But the reality is grid forming controls, I think we've also shown that these can be implemented on practically every inverter technology, and they can also operate sort of even though they're grid forming inverters, they can operate sort of in a grid following mode. And so really our biggest challenge is migrating these inverters to have that capability that would enable us to get to the 100%.
Okay.
Next question in here, did you experience any stability issues on your test system when we ran it for extended period of time with 100% inverter base? So we did not, because the control algorithms are fast enough to deal with any nominal steady state or dynamic changing of loads. It could handle all of those just fine. Now, we did not run it under any fault conditions, so we didn't have an instantaneous fault and see how the system would respond to that. But I think we have enough experience to say that if you design your controls correctly, you can design a 100% inverter-based grid to maintain stable operation under normal operating parameters.
So one plea on behalf of the community also, as you start this big center, is it would be good to put out by NREL and by the consortium some of those publications which claim that.
Yep.
It really would be helpful so that people don't rediscover the wheel, right? And
right.
I know it's a big job. Yep. None of us do it well, but I think it would be good to do. Yeah. Because
one of the
we just described now.
Yeah, because I think one of the things that we'd like to do once we get the consortium stood up, we'll have a web page where we'll have a lot of these topical things with the papers associated with it, so people can come up to speed a lot more quickly than they can now. Okay, let's see. Next one.
There are a few more, and we have like 5 more minutes. That's it.
Yep. What are the pathways to getting these guidelines from researchers to regulations? Yeah, excellent question. I mean, I'd say the group that's working on this consortium has got a lot of experience on how to take research results and get it into standards organizations. And once you get it into a standard, like, for example, 1547, I've actually worked on that particular standard since 1999. So I've worked on one standard for over 20 years, but that's the rules and regulations of how you integrate distributed resources with power grids. And we have updated that standard many times over that time period. But we take research results, we push that into the working groups, we get that formalized into standards, and then the regulation bodies can then adopt those standards and then make those requirements. And so we have a good pathway of how we get that. Now, unfortunately, it's not a quick pathway. But what we're working with inside this consortium is trying to figure out how to streamline that a little bit more so that we can get the research results implemented in standards and products much quicker than typical. Okay. Is there a formal definition for grid forming inverter? Not as far as I know. There are a couple of definitions out there. We probably will try to hammer that out a little bit more over the next year, because that's something that people are sort of asking for. But there's some interesting definitions out there around how you define that grid forming capability, as well as all these other things like offering fault ride through and virtual inertia capability don't necessarily equate to grid forming. You can deploy those kind of features in a grid following inverter technology. In fact, they're deployed right now in grid following technologies. Okay, let's see. Cybersecurity. I'll just say that we are working on ways to ensure that, because if you think about deploying a lot of these inverter-based resources, they need to both operate, and a lot of times the most efficient way of operating is with some level of communications to them. so that if you detect some kind of cybersecurity incident, you could have things run. It may not be in an optimal mode, but it'll be in a workable mode. Okay, let's see, a couple more here. One on one looking at the differences between grid forming in complex network compared with smaller island grids. I mean, this is really the big challenge that we have now, because we know do grid forming inverters on small island power grids. That's how they've always worked anyway when you have an independent power system. And so we know how to make if you just have, let's say, less than 10 inverters, then you know how to make it work, because you can talk to each one of them individually. You can have them all come to a centralized control mechanism for an island power system, and it works just like a hybrid power grid. And you can have a master device that's providing AC waveform. It's when we look at these really big distributed grids and you have lots of things interacting, that's where the complexity occurs, and that's where you have to start developing the rules of the road for how these would all work together.
Ben, just to mention something, because I know there are people from MIT Lincoln Lab, we have a little bit opposite experience with very small tactical microgrids out in the boonies. There are different questions. Those really interact also very fast, and you have harmonics and things like that. So it depends on the quality, power quality that those grids need to provide. Otherwise, it's, I think, having a lot of power electronics is going to create a lot of harmonics, and we need to deal with that. So, so I would say both complex networks, how do you interconnect them, but also how do you meet the quality of service and the interoperability standard that you promise. It's actually not, we have several people at MIT working on this. It's not an easy question either, just.
Yeah.
And maybe just one more, sorry.
Well, I'll end with the very last one there around inverter controls and do they need retuning? And so the answer is yes. Right now, you need to do a lot of tuning on your inverter controls to get these systems to operate stable. So what we're trying to get to is a little further down the road where we come up with a set sort of standard regulations on how you do that tuning. But right now, you're still in a phase where you need to do a lot of tuning to get all your controls to work properly.
Well, I guess that's because they're sort of constant gain, but you know, there's a lot of nonlinear adaptive control that can overcome that problem. And again, people are working on that. So I really wanted to thank you, Ben, we made it through all the questions. I wanted to thank you so much for kicking this seminar series and sort of giving us, it's really a wonderful thing if you can manage to put academia and active people so that we get in 15 years from here to there. It would be unbelievable. So thank you so much. And if people have some questions, we can still forward them to you. I don't know, you can send it to Dan and me, and we'll filter them. We can't promise everything, but we would very much like to. I think there was a question from Annie Weathers from MIT Group 47 in Lincoln Lab. Oh, that was the cybersecurity thing, right? Yeah, so you answered that. So I think we are all done. Everything planned well. We answered all the questions, and very much appreciated on behalf of community.